Welcome to Fun with Science. My name is Mr. Ross, and today we're going to discuss bridges. And my civil engineer helpers this morning are
Melissa?
Caitlin.
Caitlin. All right, bridges are important. If it wasn't for bridges, we would have a hard time getting across the Merrimack River, and things would be a lot different in the city of Lawrence. Okay. Before we get into the bridges themselves, we need to discuss a little bit about the different forces that act on bridges, right, and why they're built, and that determines why they're built the way they are. Right. The first one is something called tension, and we take that piece of string. What tension is a stretching force, right? You hold on to it real tight, and if we pull on it, and the more I pull, the more force I put to it, the more tension that I have. Now, this little piece of thread, if we pulled hard enough, we obviously could break it, right? Because something called the tensile strength is not very high on this thread, right? So what we need to do is, if we're going to use this for building bridges, we would want to be using a steel cable, right, which has a very high tensile strength, and we can put a lot of tension or a lot of force on it without it causing it to break. The other force, another one, which also starts with a T, is torsion. You know what torsion is?
No.
It's another T. It's twisting, right? If I take this piece of cardboard and I go like this with it, right, and twist it, that's torsion, right? I can twist it either direction, right? And that's another force that can act on a bridge, is torsion. If this were the top of the bridge where we were going across it, right, which is called a deck, right, it can twist like this, and we would need to take that into consideration. Now, but also look at the piece of cardboard. If I take and try to go this way with it, putting force pulling down on both ends, does it
No, don't.
doesn't bend as easy. All right, it bends easy this way, but this way it doesn't bend very easy at all. So what I can do then is, if I were to take two pieces of cardboard and I were to glue them together, right, and if this one tries to twist, right, the other one is going to hold it, so that I can come up with some sort of a device with two pieces of cardboard so I don't get that torsion, and it also makes it a little bit stiffer. Right? If this one tries to bend, then this one's going to hold it. Right? The other one is compression. You know what compression is?
When it
It's
goes together?
squeezing it together, right. If I take this cardboard and I squeeze it, look what happens.
It goes up.
It goes up?
It goes up, it bends, right? Now, contraction, what's contraction?
Pulling it apart.
Going together.
Shrinking is right. If we were to take this piece of cardboard, in here is pretty warm, has a certain length, it has a certain width, and has a certain thickness. We take it outside today when it's real cold, it's about -1 out there. It's going to cool down, and when it cools down, what's going to happen to the material? It's going to start shrinking, and it's going to contract a little bit. It'll get a little bit shorter, it'll get a little bit narrow, and it'll get a little bit thinner. Right? Not to where we can see it, but it does happen. Okay? What about in the summertime if we were to take it out? We're in here where it's air conditioned, and we take it outside where maybe it's 98 degrees.
It's going to get bigger.
It's going to get bigger. It's going to expand, right? It's going to get wider, it's going to get longer, and it's going to try to get a little bit thicker, right? So we have two forces, one called contraction, where it shrinks, and another one called expansion, where it's going to get bigger. Right? All of those are important when we go to build a bridge. Right? We got tension, which is the pulling, right? We got torsion, which is the twisting. We got compression, where we're trying to squeeze it together. And we got contraction, where if it cools down, it's going to try to get smaller. And we got expansion, where if we heat it up, it's going to try to get bigger. Those are all forces that are very necessary in a bridge. What's this thing?
Cardboard.
It's a cardboard.
Square.
It's not square, it's a rectangle, right? So if I were to take this rectangle and I were to try to go like this with it, what happens to it?
It
Then
makes like a
it's
diamond.
It becomes a parallelogram, right? So if I were to take and try to use this to put some weight on top of it, what's going to happen to it?
Just
gonna
It's going to fall over. But if I take that same rectangle and I do this with it, and I put some little ribbon down between it, right? What happens when I take and try to make it go over now?
It don't go.
It don't go. What happens to these
They get loose.
What happens to it?
They get loose. One gets tight and one gets loose.
One gets tight and one gets loose, all right? So what we're doing, we do that when we squeeze it like this one gets tighter, right? When we put tension on it, right? So if this were a steel cable, right, it would keep this thing from going this way. When we try to make it go the other way, this one gets tension on it and keeps it from squeezing over. So if we were going to try to use this triangle, kind of a rectangle affair, right, to build a support for a bridge, we would put some cables in there like that. Right, what shape is this right here?
Triangle.
It's a triangle, right? Okay. So, now, that's pretty good, right? If you don't push on it too hard, right, it won't collapse. But this one over here, I pushed on too hard. What's happened to it?
It collapsed.
It collapsed. The sides collapsed, right? The whole business collapsed. Will you hand me one over there with the... Now what I've done is I've replaced my little ribbon or my cable with a piece of cardboard here and a piece of cardboard here, right? So now then, this makes it much stronger, right? And I've also put some pieces of cardboard in here, right, to keep the sides from collapsing when I push down on it, like this one. Right, this one won't happen. Right, we can put quite a bit of weight on there. Of course, anything we can always destroy, right? Even the strongest bridge we build, if we put enough force on it, we can destroy it. All right, what I want you to do, we have a little bridge here. I want you to run the car over the bridge and see what happens, right? You're a speedy driver. Drive slowly, will you please? Right. So what happens when the car gets in the middle of the bridge?
It sinks in.
It sinks
yeah.
down. Now, would you want to drive across that bridge?
No.
I wouldn't even want to walk across that bridge. So what we're going to do is, if I take this piece of cardboard now, and I put another piece like this, and I were to run the car across it, what's going to happen?
It won't sink in.
It won't sink down because we can't bend this piece of cardboard in this direction, right? And if we have to put it up here like this. So what we can do is we can build a thing called an I-beam, all right? It's called an I-beam not because it has eyes, but because the shape of it looks like capital letter I, right? Now, that's got a piece of cardboard here, a piece of cardboard here, a piece in the middle, and that's pretty sturdy. And if I take two of those and put them up side by side like this, right? And I put my bridge deck on top of it. Now then, my car sat there, and we can get quite a bit of force down on this. If I push down on it, right, it's pretty sturdy. Right. This particular bridge is probably the oldest kind of bridge in the world, and it's called a beam bridge because of the two beams, right, underneath it, down here. Most likely, in the way this bridge was designed first was, it wasn't really designed, a tree fell across the little stream, and some caveman came up and said, ha ha, well, I want to get my feet wet, and he walks across the log, right? And then later on, where the trees hadn't fallen across, they said, well, okay, we got to do something. We'll chop down a tree and throw the log across, right, and build ourselves a little bridge. And they said, well, one log's good, two must be better. So they put down two, and put some sticks across it to build the bridge deck, right? Make it a little bit wider so they can walk across it. Then, somebody come along and invented carts and horses and all those things, so they had to even make them wider, a little bit stronger. Beam bridge. Now, do we have any beam bridges around here?
I think so.
It's the most common bridge we have.
The Green Bridge.
Not the Green Bridge. The double-decker bridge is a beam bridge. Right? If you drive along the double-decker bridge over here on 495 and you look up and you see all the beams up there supporting the top deck. Anytime you go drive down 93, 495 and in the major highways, the little bridges that cross over them, right, those are all beam bridges, almost all of them. And the reason they're beam is because they're easy to construct, but you can't run them for a very long period of time, right? The distance between the support here and the support over there is called the span, right? On a beam bridge, span's about 250 feet. If you get any longer than that, the beams start to bend a little bit. They start to give. and so the bridge becomes unsafe. So if you look at them, the ones that go across 93, right, they have supports on each side of the highway, and what's in the middle?
Beams.
There's another support, right? Right in the middle of the highway, where the highway divider is, there's some more pillars that go up to hold up the center of the bridge, right? Because we don't want to get the span too wide. Now, if I were to take this bridge, this beam bridge, and I fasten it down over here on this support, so that this end doesn't move, and I fasten it down over there on that end, so that end doesn't move, what's going to happen to it?
It's gonna be like
Hmm?
it's gonna be like a bridge.
It's going to be like a bridge. I'll fasten it down so this can't move and that end can't move. What happens today when we go out and it gets down to 1 degree zero, or even gets colder? Let's say maybe it goes down to -10. What's going to happen to this bridge?
It's gonna shrink.
It's going to shrink.
Fast.
Right, so if it's going to shrink, then this end's fastened down real tight and this end's fastened down real tight.
It's gonna be harder to shrink.
It's going to be harder to shrink it, but that shrinking, right? That contraction of that bridge puts a lot of force on it, right? Which puts a lot of tension on this part. And what's going to happen is that it's eventually going to pull apart. Right? So, we can't fasten it down. Likewise, we fasten it down real tight, and in the summertime, when it got to be 100 degrees out, or if we go down to the desert and it's 110, what's going to happen to it?
Expand.
It's going to expand, and if these are fastened down, it's going to try to push the ends apart, and it's going to cause this thing to bow up a little bit and break the bridge. So, if you look at these beam bridges, right, the ends of them aren't fastened down real tight. They're bolted down so that they can't jump up and down like this, right? But they're not bolted down real tight, and they're allowed to move a little bit. So that whenever they expand, right, the bridge gets a little bit longer, right? It doesn't bow up in the middle, and then when it gets cold and it contracts, it allows it to get a little bit shorter. And if you drive across them, like the bridges going across 93, right, if you get into the middle where that support is, you'll see a little metal piece, right? It's called an expansion joint. And that's allowed to slide back and forth. Like every time you drive across it, you hear a little bump, 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 bump. And so that's that kind of a bridge. We have another bridge, and that's the double-decker bridge going across the Merrimack here in Lawrence, and also all the bridges you see going across the interstate highways are like that. We have another one. What do you think this one's called? What kind of bridge is this?
The arch bridge.
It's an arch bridge. Now this is the next oldest probably kind of bridge, right? And the Romans used this a lot because of their little arches, right? And what it is if you squeeze down on it, the arch is pretty strong, right? And it's able to support the bridge. Again, we're going to have some expansion and contraction we have to worry about so that it's not really tight. This bridge can be a little bit longer between spans, right? From the support to support. What's a span? It's from where it's fastened here to where it's fastened over here, right? That's about 250 feet. On the arch bridge, it could be about 800 feet. So it's another kind of a bridge. Well, let's leave this one. Now, this one is called a truss, T-R-U-S-S bridge. Right? What shape is this?
Triangle.
Triangle, right? Have me that triangle over there. Triangles are strong. Right? You take this triangle like this, I can put an awful lot of pressure down on that triangle without anything happening. What is happening is as I press down, right, I try to compress this side, I try to compress this side, right, and if it wasn't for this bottom piece, those two sides would go out like this, right? So what I'm doing is putting some tension on this bottom piece, right? But it's a strong structure, right? And if you look at the truss bridges, basically, they're it's a whole bunch of triangles. So this bridge then can support an awful lot of weight, okay? And the truss bridges, where do we have one in Lawrence? You said it before. The Green Bridge.
Oh, the green.
If you look at the Green Bridge, isn't it a whole bunch of triangles, all right? There's a whole
Yeah.
bunch of beams and stuff put together, right? Which are called a truss when we do that, when we put all these beams together to make a rigid structure, that's a truss, all right? And the Green Bridge going across the canal over here is a truss bridge, right? This is going to be a little bit longer still, from about 100 feet or so up to about 1,600 feet. Right? So this is a pretty strong bridge. We can run the car across it right, without too much problem. And we also, on that bridge, we have to worry about the expansion and contraction due to the heat, right? So that it's not fastened down real tight either. It's allowed to expand and it's allowed to contract a little bit. Okay? What about this one?
Golden Gate Bridge.
Golden Gate Bridge. All right, this is the Golden Gate Bridge. It's called a suspension bridge. Okay? On the bridge, there are towers like this, right? There's one huge cable that runs from one end of the bridge up through the tower, back down to the other end of the bridge, one on each side. And then there are little smaller cables running up and down, which are the suspension, holds the bridge deck. And remember, the bridge deck is the surface that we're going to either walk across, run our cars and trucks across. And what is happening here is this white styrofoam is like a big block of concrete or rock, right, which holds this end very steady so that it can't pull, right? And the same thing on the other end of the bridge, a big block of concrete that holds this down. Okay? So what has happened, the way this bridge is supported with these towers. All the weight of the bridge and the traffic coming across it pulls down on these cables, right, which pulls down on this cable, which pulls down on this tower, right? So what it's trying to do is force this tower down into the ground. Same thing with this tower. So all the force to hold the bridge up is with these two towers. The reason the big block of concrete's on each side is we want to keep the forces balanced. This is all a balancing act on this suspension bridge, right? If this tower were allowed to go this way, well, guess what happens?
Fall over.
The whole bridge is going to come down, right? So it's a balancing act. We're going to need to keep the force on each side of these towers equal so that they stay straight up. Okay? Now, these bridges are the longest type of bridges that we can have. This can go up to like 7,000 feet, over a mile long. Right? Now, back in 1940, you remember 1940, right?
No.
If you don't remember 1940, out in the state of Washington, they built a bridge, suspension bridge like this. Brand new bridge. All the engineers did all the design work and everything. And one day it started to rain a little bit, the wind blew a little bit, not very hard. Right, and all of a sudden this bridge started doing this. It started going up and down and twisting, and pretty soon it just collapsed. Have any idea maybe why?
Because it wasn't strong enough.
Oh, it's strong enough. Right?
Wasn't
But
balanced.
that's a good thought. Huh?
It wasn't balanced.
Well, yeah, it was all balanced up and everything. They did all their math and they did all their things. What it was that they didn't consider is something called Bernoulli effect, right? Which is the same thing that makes an airplane fly, right? The wind coming across, or the air coming over the top of the airplane wing causes the wing to lift up, right? The same thing happens on these cables. As the wind comes across, right, and it had raining a little bit, and there was a little bit of water running down the cable, right? So then it was shaped just right so the cable would come up and the wind blow across it. When it came up, the little rivulet of water that was running down changed, right, and it's decreased the lift on the cable, so the cable fell back down again. And the cables got to go on like this, right? And as soon as these cables started bouncing up and down,
The whole bridge.
the whole bridge started going up and down. So they had to rebuild the bridge. And they found a solution to it. What do you think the solution was? That's a tough question, right? Right. The solution to it was to stop the little rivulets of water coming down it. Right. So what they did is, in this big cable, they wrapped a smaller one around it, which broke up those water running down it. Right. So that when the wind came across, right, it didn't change the lift on the cable, and it didn't start going up and down like this, and the bridge wouldn't fall down. The second one they built is still there, by the way. So, suspension bridge, distance of 7,000 feet. All right. Between spans, what's a span? It's the distance between the supporting elements. In other words, from here to here, we can have 7,000 feet distance. This is the longest kind of bridge that we have. All right. Let's get rid of some of our bridges. We don't need all these bridges. Okay, this bridge is probably now our most famous bridge because everybody knows where it is, what it is. And this is the Leonard P. Zagan Bunker Hill Bridge, right down in Boston. This is a brand new bridge they just built. And it's a kind of a suspension bridge, right? Because it has towers, like the one we had up here before, and it has cables which are holding the bridge up. So it's a suspension bridge of a kind. And it's a special kind. It's a cable-stayed bridge. It's stayed because the cables hold it in place, make it stay where it's at. Okay. Now, this bridge, the span on this bridge is not quite as long as it is on the old-fashioned suspension bridges, right? Because this can go from 500 feet up to about 2,000 feet, right? Where that old suspension bridge was like 7,000 feet. But basically the same concept. We have a tower, right? We have cables on the tower. Again, it's a balancing act, right? What we want to do is, the weight of the bridge is putting tension on the cables, right? The cables then are pushing down and trying to compress this tower down into the ground, right? And the same thing on that end. There are 24 cables here, there are 17 cables here, and 17 cables over there, right? Now, you've all seen pictures of this thing. It's lit up at night, right? Each one of those cables has a little spotlight on it to light it up so that we can see it at night, make it look much more impressive, right? The cables themselves are covered in plastic. That's why they look white, right? What do you think's on the inside of them? Steel, right? Because there's a lot of tension. This has got to hold all this bridge, these cables do, and plus all the traffic. So there's a lot of tension. So we want something with a very high tensile strength. So in this cable is little steel wires, okay? And to make up the cable, to put several steel wires in there, right? To make up a strand, and then each cable has several strands in it. This is the north end of the bridge. That's the south end. This end points towards that. That end over there points towards Boston, right? As you're going from here down into Boston, you go across the bridge on this side and down over into the tunnel, which is where I got lost Saturday, right, going into the tunnel. But anyway, this bridge is a little bit different. This is not the biggest stayed cable bridge, right? There are some much bigger than this. But this one's a little odd. It's a little different. Over here on the outside of the bridge, there is another couple lanes for traffic, right? If you're going to take a look at it here, this side here, right, on the outside of the cables are there for another 2 lanes of traffic. That's called a cantilevered section. This here, and what they have is some little beams come out. Notice, and this is just sort of hung out over the edge. Okay. Now, so what we have is the tension pulling down on the cables, which is trying to compress the tower down into the ground, and there's a balancing act. The force on the tower this way and the force on the tower this way has to be equal, or what's going to happen to that tower?
It's gonna break.
It's going to fall over, right? And we don't want that to happen. The whole thing will come down. Now, We have the same problem with this bridge as they had with the suspension bridge, with the wind blowing across it. And if we don't do something, what's going to happen to those cables?
They're gonna fall
They're
over.
going to start going like this, vibrating, and the whole bridge is going to fall down. So each one of these cables then has that little smaller cable wrapped around it to break up the water going down it. And in addition, down on the end of the cables now, what they did, they've added like a shock absorber on your car. Something to take up the shock, right, to keep the cables from vibrating. So on the end of each one of these cables, there's a shock absorber. You have a question? No questions yet? All right. No. Underneath the bridge runs the orange line, which is a subway line, tunnel, right? And it runs very close to one of these towers. Right? Now, this whole big bridge up here, right, is pretty steady, but it does move a little bit. So this orange line is running within inches of one of those towers when it goes down into the ground. Right? So if we were to all stand shoulder to shoulder like this, and you were to move a little bit, what's going to happen?
We're gonna fall in.
Well, you back and forth this way?
We're all gonna move.
We're all going to move, right? So if that tower moves just a little bit down in there,
The whole
and it was
bridge-
right up against the tunnel, what's going to happen to the tunnel?
It's all gonna
Gonna
move.
It's going to move the tunnel. It's going to collapse the tunnel, right? So what they do is coming down, right? These towers, when it goes down into the ground, right? It's set in a little cylinder, right? Which gives it a little space. So if we don't stand shoulder to shoulder, she can move back and forth a little bit, and we don't have to move, right? So they do the same thing here with these towers. They're set in little cylinders, so when they move back and forth, they don't push the dirt, right, and collapse the orange line tunnel. We don't want to do that. We don't want to mess up the subway system. Another question. On the south side of the bridge, the Charles River runs through. Okay? And there are holes down through the center of the bridge. What do you think they're there for? This is one of the things that the engineers, when they design the bridges, have to think about, right? Why do you think they put those holes in this, right in the center of the bridge?
Maybe if it rains, the water can go through.
Right, if it rains, the water goes through and runs down into the Charles River. That's a good thought, but what else is on that bridge besides water?
Cars.
Cars, yeah, okay, there are cars
People.
there, and people, but the cars, when the cars are running up and down, right, they're going to leak a little bit of antifreeze.
And
They're going to leak a little oil, right? And if it rains and you let all that water run down into those holes into the Charles River, you're going to pollute the Charles River. Plus, right now, when it snows, they're going to put salt on there. Do we want all that salt in the Charles River?
No.
In fact, those holes, if you come across the bridge, you find them. They're got big concrete barriers up so that the water doesn't run down in those holes.
Oh.
Why else do you think they might put the holes there?
So when it gets cold.
Because of the expansion
Yeah.
and contraction? Well, there are expansion and contraction joints. But let me tell you, all right, I won't torture you anymore with those holes. They're there because of the alewife.
The
What's
what?
that?
The alewife, right? The alewife is a fish, right, that migrates up the Charles River
And it has their babies
to spawn, right, to lay eggs and to have the babies.
in the summertime.
Right. The alewife only migrate during daylight hours. So if we put this big bridge up there, and this is a good-sized, wide bridge,
The
here comes a
shadow.
little alewife swimming up. He's going to go, spawn, and it sees the shadow of the bridge and says, "Whoops, it's night. I got to stop. I got to wait till morning."
So
Well,
then
morning
the-
never happens, right? So what they had to do
So the
is so that
sunlight
the
could go
alewife
through.
could go up the river and spawn, right? They put those holes in so the sunlight would come down and light the river up before, and the fish say, "Ah, it's daylight. I can swim up." Right? No problem. All these things, when you're a civil engineer like you are, you have to consider when you build this. One is the tunnel underneath the bridge, the alewife, right? You don't want it to run off on the bridge to pollute the river, right? But you need to put those holes in there for the alewife so that they can have sunlight. Questions? No? No questions. All right. So let's go back to what we have, all the stresses on the bridge now. We have tension, right, which is the stretching of the cables, right, pulling down on it. And we want to make those cables strong enough, with enough tensile strength, which is how strong they are, so that when we pull on them, they don't break. Right? The other one is torsion. What was torsion?
Bending.
Yeah.
Twisting,
Bending,
right?
twisting.
Twisting, right? That's torsion. Right? Compression, which is
Bending.
squeezing it together, right, which would cause it to bend. The other one is contraction. What causes contraction?
Shrink. The cold
Cold
weather.
weather.
The cold weather causes it to shrink, and expansion
It
When it gets
separates
hot,
in
is
the
it?
when it gets hot. And then we have all of our different kinds of bridges. The first one, probably the oldest one, was called a what? What was it?
Double.
an I
It's an I
but,
beam.
beam.
I-beam. So the oldest, probably first bridge was a tree limb or a tree trunk falling across a little stream of water, right? And the caveman walked across it, right, because he didn't want to get his feet wet, right? And he didn't want to have to throw his coat down for the girl, being chivalrous, right? So this is probably the first one, and it's called an I-beam because the
It's
shape of
shaped
the
like an
beams,
eye.
right,
Like
usually
an
are eyes, like a capital I. Okay. Do we tie down the ends of this beam?
No.
Why?
Because when it moves,
Contraction and
For
expansion.
cause
Contraction
contraction
and
and expansion. We want it to be able to expand. We want it to be able to contract a little bit without putting a lot of stress on the bridge. And so it's allowed to move. The next one is what? What's this one called?
triangle bridge.
No.
Truss. Truss. This is truss bridge,
truss
right? What truss is a collection of cables and beams and so forth that make a rigid structure, right? And this is like the green bridge that we have down in here, right, in Lawrence, right? And it's a truss bridge. And if you look at it, there's probably on top of it, there'll be pieces going across to keep the bridge from, going this way on it, right?
Golden Gate Bridge.
Golden Gate Bridge, which is a suspension
Suspension.
bridge, right? Because it's all suspended with the cables and from these towers, right? And we want to keep the towers straight up, so we got big blocks of concrete on either side, a rock where the ends of the cable are like this, and it's all balancing act, right? We don't want too much stress this way because what's going to happen to this tower? It's going to fall over. Or too much stress the other way, the tower is going to fall over and it's going to collapse. Now, this bridge has a little cable running around the big one. What's the reason for that?
For the
Rain.
rain.
For the rains and
So it doesn't.
and the wind.
It doesn't.
Yeah.
Yeah, it breaks up the water running down it, so when the wind comes across, it doesn't get that cable going up and down. This is the longest kind of bridge that we can build, the longest span. Right? It's a way you can build a suspension bridge with more than a mile between the two towers, right, which would be the span, or between the end and the tower, which would be the span of the bridge. And this one is, what's this one? This is also a suspension bridge, but it's a special kind of suspension bridge, which is a cable-stayed bridge. It's hung up here on cables, and it's kept from going side to side and up and down with those cables. It has the same kinds of problems as that suspension bridge. We could have wind coming across and little rivulets of water running down and make the cables start to vibrate like the strings on a guitar, right? Which would eventually cause the bridge to start bouncing up and down and ultimately collapse. On the ends of the bridge, these cables have little wires around them, little smaller cables wrapped around them to break up that stream of water. They also have shock absorbers on it to cause the vibrations to dampen out. Again, it's a balancing act. We want this tower to stay straight up. We don't want it to fall down this way or that way, right? So this cables have an equal amount of force this way as they have that way, so the tower remains straight up. The bottom of the the bridge is in a little cylinder. This tower going down, it goes into the ground, it goes into the little cylinder. Why is it going into the little cylinder?
So for the fish.
L wife.
Oh.
No. Why is the little cylinder there?
So,
Because the
oh.
orange line runs underneath
Yeah.
there, right? And we don't want the tower to move a little bit and collapse the orange line, so we put it in a cylinder, give it this little small space, doesn't have to be much, so that it doesn't push the dirt and collapse the orange line. The holes, why are the holes there?
For the fish.
For the
For the
alewife.
fish, right, the alewife, right? Because we don't want the alewife to think it's dark because of the shadow of the bridge. We don't want them to think it's nighttime, so they go upriver and spawn, and we get new little alewives. So I think that's probably the end. We had all these different kinds of bridges. They all have some of the same basic problems, engineering problems, but they're a little bit different, and we use the different bridges because of the capability of the length of them. Okay, that's it for this week, and next week we'll have another exciting Fun with Science program for you.